say thank you for coming. We appreciate your time spent here, and it really makes this much more meaningful. The students have an audience, so I do appreciate you being here. Again, after this presentation, after the demo, you can talk to the students, just ask them more questions and something comes to your mind, and then we'll just be wrapping this up. So this is our last presentation. This is a group of four-year students. It's a mix of electrical students and electromechanicals, and we're going to let them describe what they built.
Good afternoon, everyone. I'm Remillard. This is Windsor and Paul Z. And we did the Alien Invasion, the room size of the game. So a little bit of background. Our game is basically modeled after Battleship, and this is just showing different ways that people have manipulated the game in the past. Over here, they're actually in their boats, throwing a ball over a barrier. And over here, they're playing more of like a Pong-style game where they throw over into a cup. This is our game. We have humans on one side and our device on the other side playing against each other. We don't have any barrier in the middle. This scoring will depend on how accurate you throw the ball, and that will be explained more later. Each team will have 10 boxes to make their own ships. And we're using rice balloons as our projectile. So look at the problem statement in the previous slide that Brad showed you with our game. To give you a little more detail as to what we needed to solve. So we needed something that was very accurate automated boxer against the human beings. We also needed something that automated hit detection to figure out if it was a hit or a miss. An LED scoreboard to display the exact hits or misses. And easy setup, and the reason for that easy setup is to eventually we want actual high school students to actually play this game and to show what 4-year degree bachelors in either electrical engineering or electrical mechanical can actually build. So our solution statement of what we were going to make in order to solve those problems were an alien launcher, and that's a trebuchet mechanism that is on a belt-driven car. The hit detection, as you can see, is webcam using image processing software and an LED scoreboard, and again wireless connection, so it's an easy setup for high schoolers to set up themselves. So just to look at a simple, very simple diagram, we're going to dig real deep into everything here. But here you're going to have your Raspberry Pi looking over the playing field. Obviously you can see your human beings on this side. I wanted to emphasize right here, and this dotted line that goes around in the square represents the trebuchet on a cart. Oops. And here's your counterweight on this trebuchet arm. It pivots. So the more angle that you put on that trebuchet arm, obviously the furthest your projectile is going to swing around into the human side. You're going to have a motor driver bringing that arm back to a certain angle, and then you're going to have your gear as well right here. Oh, again, just to show you, this is an overview, this is just a side view, not confused. Alright, so for the overall design, we went with a trebuchet, but there was other options that we could have gone with, like this catapult. We didn't go with the catapult because they used torsion, which is basically a bunch of ropes that the shaft is in, and it uses the torsion strength from the ropes to throw. The trebuchet is just much simpler. All you need is the weights, the arm, and the shaft pretty much, and you can't get any more simpler than that. So we need a little validation that the trebuchet actually works. So we just built a quick one and did some testing. Right here is the actual range that we got from throwing the projectile. Our projectile is not very big. It was 0.024 kilograms, and we did some changes after every test. So like right here, we made the arm longer and longer, and then we added more weight. And our desired length was 20 feet, and we only got to 200 inches, which is 16 feet. So we knew we needed to make some changes. So I started calculating why we didn't get to 20 feet, and I first off this equation, which we knew every variable in there except its E, which is the efficiency of the whole trebuchet, like friction loss and all that. And we didn't know that, so I just guessed 25% of it, and we came out to 20.9 feet. So we should have thrown our 20 feet if we were that efficient, so we weren't. So basically what we needed to improve on was the efficiency and also making it a little higher just in case we didn't pick up every inefficiency. After we did that, I started doing some testing because the way we had it set up is this is 10 feet from the front of the playing area, so it actually has to throw 20 plus feet, 10 to 20 feet. So we wanted to see if you could pull it back to a certain angle and throw if that correlates to how far it goes. So at 50 degrees back, it went 9 feet, all the way up to 110 degrees down, it throws 22 and a half feet. So that was good for us. That means that we could actually use this the way we had it done. The hardest part is ratcheting the trebuchet automatically. So we started talking and we came up with a whole bunch of different ideas. The one that stuck out was this Spectre gear. And basically, we're going to have it's hard to see, but there's another gear that meshes right there. It'll be on the motor, and it'll turn down, and as it turns, it'll cock the trebuchet back, and then once it gets to its final position, we're just going to have like a push board there so that you can push on it, and that'll release the trebuchet. For the electrical design, we're going to have a keypad to type in whatever coordinate you want, and then the freedom board is basically the brains of the whole operation. It controls everything for the motor driver for that motor with the Spectre gear to the servo for a feeder. It'll control all these parts, motor driver, and the trigger. So it pretty much controls everything that we need it to do. And we're also going to be communicating with a scoreboard so that when we make a hit, it's going to tell us that we made a hit and that we should change our strategy to try and hit around. I'm sure most of you know, like when you play Battleship, you do kind of a random guessing, and then once you make a hit, you hit the square next to it or on top of it or whatever. So you don't just want to keep doing your random shots. The software concept is pretty straightforward. It's going to take about 5 seconds for Ollie to get us in the right spot. The arm set is going to get us to the right angle. Loading shouldn't take too long. Then we're going to aim us getting right to the right angle. And then firing should just take 1 second.
So my job is making cars for our trebuchet. So that's how our trebuchet move forward and back to the home position. So if you guys see this picture here, we saw it in our road games and Brad explained for you guys. I just add the red line here, the red box, which is my cars we're gonna do. And then I zoom in to explain guys what we have. So we have timing belt, we will have triangle system. I will go more details in my next slides. And then we have here 10 feet, which is help our trebuchet move and always back to the whole position, which is going to be the first position. And then I have here timing belt. I have here pulleys. Here's my cards. So I explain here more details for the cards. So I have here the thickness, which is 5/8 inch. And then I have here the surface area, which is 19.5 inch. And then I have 2 steel rod, which is built 3 people in, and then I have 8 shaft, collar, and 4 flags. And here's, I zoom in my driving system to show you guys what I have here. So I have my motor, connect with the police, go through the complaints and the Excel. And then my motor is connect with electric, which is I will go soon talk about. And here's I found the motor speed to see how fast my trebuchet goes. So I found 24 inch second for linear speed. I found the circumference, and then my motor speed, which is the linear speed divided by circumference. And then I got 240 RPM. And then I use the spring scale this to know how many force I will have. Then I found 330 Newton, and then I compared to pound. And then I found my torque, which is 107 ounces per inch. And then why I do my speed mode and torque to know what kind of motor I need to use. And then why I need 240 RPM, and then my torque I need 100 also. So I found 210 RPM, which is slow, but it's fine because it has more torque, which is 165 volts, which is really good. And then I use the microcontrol as the 13 amp because my motor has 5.5 amp. And my electric side here, so I have full position scissor with keypad, connect with microcontrol, and then that connect to motor control, which is the turn our control my motor on. And then there, my microcontrol with motor control connect with 12 volt supply. And here's my software. So I use C programming to write my software. So my code is always starts. If I click key 1, it doesn't do anything because my cards will be in the first position. So if I click key 2, it's move 1 feet in the second position. So same thing with all the numbers in my keyboard. So if I need to back, I click B. That's only help my trebuchet to back in the first position, which is the home position. And I always start the first position.
So to dive into the score system, electrical design, which is what I was in charge of. So say it's the trebuchet launcher's turn to go. So it aims the coordinates, say it's like A5 or something, and it talks to the Raspberry Pi through the scoreboard micro, and the Raspberry Pi will look down onto the field and say, hey, A5 was hit. So it returns the results and tells the trebuchet, hey, there's a ship there, maybe you should go to A6, or how the battleship game goes. And then the human side will have aim coordinates after that. Okay. And right here, you'll have your scoreboard. And so, again, we were going for accuracy and for the trebuchet. But again, say it hit A4 instead of A5, which is what it was supposed to hit, it still gets 1 point for hitting that location because it was that ship. And 10 points if it has to hit the exact location. To get more into the webcam mounting concept, so in the data sheet of the webcam itself, it was said that height equals width. So to describe that, so if you went up 10 feet, it would display 10 feet in the width. And I wanted to test that theory because it was kind of an importance seeing the whole 10 by 10 playing field, which is what our playing field is 10 by 10. And so I built a little benchtop testing right here. This box right here is plywood 18 by 18 inches, which means that I went 18 inches high with my beam. And just underneath this beam, you can see that there's a webcam underneath. And to test that this actually is true height equals width, I expected to see this whole board. However, that was not the case. And doing a little math, well, I got 14 inches by 14. And doing the math to show exactly how high I had to go, I got it to 13 feet, which proved the theory that 10 feet or height equals width. It's not true for that camera. To talk about the colors of the ships and the projectiles, this box distinguishes a part of ship. We can move them in any coordinate that you want. The webcam sees the world as red, blue, green, anywhere from 0 to 255. And 255 is the brighter end of those individual colors. And these red rice blues is what we chose for colors, and that's how I wrote my software, is looking for that red blue. Any other color, it doesn't really matter. The boxes, the ships, the background should not have any red. We had an actual issue with that with the layer. The lighting in the room has a huge factor, and I'll show you that in the how it's presented over there. To look at it, hit detection concept. So over here you have your Raspberry Pi looking out at the human field. It has three wires. You have your communication signal, RS-232, which is sending the signal of that exact spot. So you have H10 and I10. You have your ground wire and your power. As you can see in the scorekeeping system, which uses an Arduino, it finds those two spots and actually displays that that was it. Alright, just to show you, here's what the webcam sees right here. And as you can see, it's H10 and I10. Obviously, you're going to hit because that's red. Regions of interest, looking at just H10 itself in that little box right there. Actually, let me back up. So, the webcam breaks what it sees into 100 boxes. The reason for that, obviously, is because there's a 10 by 10, so equals 100. And when it looks in one of these boxes, so say H10, it has 12 pixels per row, 12 pixels per column, looking for just one pixel red. And once it finds that red pixel, it jumps out of the box. It already knows that there's red there. It jumps out of that box, so you don't have to look through that whole box. You can go to the next box. Just to look at the software concept a little bit, how my webcam actually works. So over here you have webcam taking an actual picture. As again, if you can remember, instead of the 12 by 12 pixels per box, so if you multiply that by 10, obviously you have 120 by 120. Takes a picture, breaks it into, looks into every single one of those boxes, which is 12 by 12. It looks at each pixel inside that box. Now with the lighting that I was in, again the lighting was a big factor in my part of the project. If red was over 240, if you can remember, every color should range from 0 to 255, 255 being the brightest. 240 seemed to be just perfect. Once you look at any of the other colors, you can send my location as to where there was a red pixel. Now continue going through this until you have actually finished going through the whole grid of 10 by 10. And once it was done, it would go back through the whole loop. Here's just a little code. Again, red when it's greater than 240, it'll send the row, which is A, B, continue on, and then also the column 1, 2. Where I'm going to show you our work breakdown structure. There's a lot here. Some of our milestones over here. Actually moved to destination right over here. Feeders
we